In today's video, we're going to be talking about forces in 2 dimensions. After watching this video, you should be able to break forces into x and y components and understand what static equilibrium is. So let's get right to it. If you remember, a while back, we studied Newton's laws, and one of the laws that was really important was Newton's second law. And basically, Newton's second law talked about that F equals ma piece, okay? And we learned how to draw free body diagrams to determine the net force on objects and the acceleration on objects. So this is actually very similar to what we were doing before. The only difference was when we were doing problems with Newton's second law, typically the forces were in the horizontal or vertical direction only. Now we're ready to start looking at forces that may not be exactly horizontal or exactly vertical, because we know how to break those forces into x and y components. So we're just kind of adding to something we've already learned. So this seems familiar to you. It is. So let's get right to it. Let's practice breaking a force into x and y components. Okay, so here is a railroad car with a force of 400 newtons that's directed 60 degrees from horizontal. Okay, like I can draw the horizontal line in here, and this angle here is 60 degrees. Okay, I want to know what is the force in the x direction and what is the force in the y direction. Okay, so to do that, and I guess let me change pen colors here. What would show up? Well, maybe blue. I'm going to look at this piece right here, this vector in the x direction, because this force is made up of a component in the x direction, and I'm going to look at this vector in the y direction, because to have a force pointing at an angle like that, that indicates that there is an x component and a y component. Now how do I figure out f sub y and f sub x? Well, I'm going to have to use some of my trig functions, right? So to find out f sub y, I'm going to use sine of 60 equals f sub y over the hypotenuse, which is 400. Notice I just have made a triangle here, basically is what I've done. I've made a triangle. So if you do that math, the sine of 60 times 400 equals an f sub y of negative 346 newtons. Notice your calculator doesn't put in the negative for you. I'm putting in negative because it's going down. The force is going down in terms of, relatively speaking, where down typically to me is negative, okay? Then for x, how do I figure that out? Well, I'm going to take the cosine of 60 equals f sub x over 400. And if you do that math, cosine of 60 times 400, I get an f sub x of positive 200 newtons. Now again, your calculator won't say positive, it's just I know that's going to the right, and so I'd call that positive. Okay, so that's breaking forces into components, and we've done that a lot already with velocities and that type of stuff, so this shouldn't be that horribly new to you. What is equilibrium? Right? Basically what equilibrium is that when all the forces acting upon an object are balanced, the object is said to be in equilibrium. The force is balanced. Okay, I mean, like, and I can do a quick example of this. Here is a table, okay, a beautiful table, and I'm going to put a brick on this table that we'll say has a mass of 5 kilograms. Okay, it's not moving, it's just sitting there, but we know that every object on Earth experiences the force of gravity, F sub g. Now what is balancing the force of gravity? Well, this table is pushing on this brick with a normal force, F sub n, and these two forces must be balancing each other. If they didn't, if the forces aren't balanced, we'd have some movement, okay? And that's not the case in equilibrium. So an object at equilibrium is either at rest or staying at rest, which is an example of this, or in motion and continuing in motion with the same speed and direction. This one's the piece that's a little bit confusing. Remember, a force causes an acceleration, and if there is no force, then there is no acceleration, and so the object just continues moving. An example of this would be, and this isn't perfect, but if you imagine standing on ice skates and someone pushes you, basically the force in the x direction, that push, there isn't much to slow it down. There isn't a lot of friction on the ice. So you kind of just keep on moving, right? I mean, eventually you do stop because there's some friction, but if we could make it completely frictionless, you would just keep on it going, okay? Because a force would be needed to slow you down, to basically cause you to accelerate in the opposite direction in which you're traveling. So static equilibrium basically says that an object is at rest, and we call that static equilibrium. Basically, the forces are balancing each other out. And static means stationary or not moving, okay? So this means that if you figure out the resultant forces on the object, if you were to make a free body diagram and add up all the forces in the x direction, all the forces in the y direction, it should equal 0, okay? So static equilibrium basically means all the forces should equal 0. So I'm going to draw a little picture here. It says a mirror is hanging on the wall in a state of equilibrium. Thus, all the forces acting upon the mirror must be balanced. Okay. So if I draw a mirror here, and let's say I don't know, for some reason I'm hanging it with like some rope, okay, from 2 bolts, okay, and this mirror is just hanging there. Okay. Basically, this mirror is absolutely experiencing the force of gravity. Now, what is balancing out the force of gravity? These 2 ropes have a tensional force, F sub t, the force of tension. And basically, that force is balancing this force of gravity. So this means that all the horizontal forces must be 0 newtons, and all the vertical forces must also be 0 newtons. Okay? Let's just take a look at another type of example problem where this time we're looking at 3 of the same picture, but basically the pictures are being hung up a little bit differently with wires supporting this 5 Newton picture, right? And what a beautiful scene it is. And you'll notice in this picture, the wires are 15 degrees with horizontal. So basically this angle here and here is 15 degrees, okay? Whereas this one is 45 degrees with the horizontal. So this angle here and here is 45 degrees. And then this one is 60 degrees, the angle here and here. I'm wondering what the tensional force is on these wires, all right? The tensional force on these wires. Because this is kind of a real, actually, engineering problem. If you were to hang up a sign with cables or wires or whatever, you would need to know what the tension will be on the cables or wires. Because some cables or wires can only hold so much, and they eventually break or snap or something. So for safety concerns, so no one gets hit on the head or something like that, you need to kind of be able to calculate the tensional force in the wire by holding up an object. Okay, so let's do that, okay? I know that this wire must be able to, or is going to be experiencing a force of 5 newtons pointed directly up because it's got to balance the force of gravity, okay? So these wires must balance the force of gravity, and in this case, the angle is at 15 degrees from horizontal. I'm wondering what the hypotenuse is, okay? And that's F tension, or how much tension is in those wires. So to do that, I'm going to basically take the sine of 15 degrees, sine of 15 degrees, equals opposite, which is 5, over hypotenuse, which I'll just call F tension. And I'm sorry I'm kind of in the picture there, but F tension. If you do some manipulating algebraically, you're basically going to get 5n over the sine of 60. And if you do that math problem, you would get a tensional force of 5.8. I'm sorry, I lied. You would get a tensional force of 19.3 newtons. Yeah, looking at the wrong answer there. 19.3 newtons. Okay? Now, the question is, as these wires move closer and closer to being vertically up and down, what happens to the tensional force? So if you want to take a guess right now in your head what's going to happen to the tensional force as we move from left to right here, that's not a bad idea. Okay, so now I'm wondering, what is the tensional force if I change the wires to about 45 degrees with horizontal? So again, here's my angle of 45 degrees. Here's my tensional force pointing up of 5 newtons. I'm wondering what the hypotenuse is, what this is right there. And basically, you're going to again use trig. And in the essence of time, I'm just going to write what it would come out to be, 5n over the sine of 45. And if you do that math problem, you would get 7.1 newtons of tensional force. what a decrease just from going from an angle of 15 degrees to 45 degrees. Here it's 19.3 newtons, here it's 7.1 newtons, okay? Same exact picture, same exact force of gravity pulling down on it, but just changing that angle causes a big difference in terms of the amount of tensional force on the wires, okay? So you could use much smaller wires here, it probably cost a lot less, to hang the same sign at an angle of 45 degrees to the horizontal compared to if you wanted it to look like this with this 15-degree angle. Let's check out 60 degrees. Again, I'm going to save you guys some time and just write out what would it end up looking like. It's going to be 5n over the sine of 60. And if you do that math problem, you get a tensional force of 5.8 newtons. Okay, and that's where that answer came from. I was looking at the wrong one. So 5.8 newtons. So notice as the angle with horizontal becomes closer and closer to being vertically up and down, the tensional force gets smaller and smaller and smaller until eventually, if I were to have a fourth picture and I just said, hey, I'm going to hang these wires just straight up and down, what would the tensional force be on those? Well, F tension would equal 5 newtons. It would exactly balance out the force of gravity. That takes care of this video. I will see you guys next time.